actually scroll up and have speedometer.
It's just like airplanes. There's a lot of airplanes that's going, they're keeping analog scales because you can glance at the meter and tell if something's wrong or right. You don't have to read it. So on all our airplane indicators, we had a big old. I'm gonna run this off and give it to you, by the way. So this is the mnemonics that they use. A mnemonic is a representation. It's a memory jogger. And this is pretty standard in the trade of what letters they use to indicate different things. So when we start looking at these diagrams, and it's the same on the Festo too. If something's designated A, it's a what? Okay, now what's an actuator? It's a unit that turns pressure into motion. Okay, so all your cylinders are actuators. All motors are actuators, right? You understand? Solenoids are actuators. So all our actuators are going to be designated A, like 3A, 1A, right? Does that make sense? Then we have B. If we see a B in the designator, that's going to indicate it's some type of sensor. What's a sensor do for us? It takes a physical quantity and converts it over to an electrical quantity, right? You understand? So our PLCs, we can control it. H is for a what? Indicator light. And K is for a relay. Okay on relays? So what does a relay do?
Relay contact.
Yeah, but it's an electromechanical device, right? We control it with electricity, but it's a mechanical device, so its contacts it's made are mechanical. Our PLC is going to do away with relays, never. The PLCs don't put out enough drive. If they did, they would be huge. Now they're little old tiny boxes, so they don't put out enough current drive to run a sure enough motor. Okay, so what that means is that we use the PLC to pick up what we call a contactor, and then the contactor can run these big high power loads. Then we have what we call a solenoid. You know what a solenoid is?
Push on.
A solenoid is a device that takes electrical. It's a linear actuator. It's a magnetic. It's an electronic device. So relays are made up of solenoids with contacts on them. Then we got S is for what? Switches. So there's all our push buttons and everything. V are for our valves. And valves are used to control the flow, right, of fluids. And then Z is our pneumatic units. Are we okay? Now, are we okay? Like I said, I'm going to give this out to you. This is the layout of the picket place section for the Amtrak line. And what they're doing is they're showing us the layout of all the sensors and the location of things. Let me move this over a little bit. So I didn't, I see what's going on. I need to do something about that. You see what's going on, right? I can't get to my drawing thing. There we go. Okay. So this is an actuator, right? And it's labeled what? 1A. So we know on our diagrams, if anything's labeled 1A, it's an actuator. And then these right here are 1D1. B is sensors. Okay. And these are magnetic sensors. So what they're doing is that the piston inside this thing has got a magnet on it. So what this sensor tells us is if this cylinder is what? Retracted. This tells us if it's what? Extended. 1D1 and 1D1 and 1D3. These are valves. Okay, you understand? These are the flow control valves. This allows us to control the speed of the fluid, which controls the speed of the actuator. So if we wanted to go a little faster, then we'd open these valves up. If we wanted to go a little slower, we would close them down, right? Okay. B1 right here, this is a what? That doesn't belong to an actuator, and we'll look at that in a minute. So an actuator circuit, we're going to identify an actuator circuit. So this actuator is actuator 1. And everything that belongs to the actuator circuit is going to start off with 1. Does that make sense? When we look at the diagram, we'll see that in a minute. So B1 is not part of an actuator circuit. Yeah. Are we okay? So this is the traverse right here. Okay, y'all understand? And here's a vacuum cup. These are the yellow lines on the drawing. These are your pneumatic tubes. This doesn't have a flow control valve on it because we're not concerned with flow, we're concerned with pressure or vacuum. Yeah, but that's not for this. That's for this guy right here. So what happens is that these two guys right here, this cylinder right here, extends this down and raises it up. So we can control how fast it goes down and how fast it picks up. The flow control, we don't have a flow control on this because it's a vacuum, right? You understand? So what we have to do, we need to be able to control the vacuum. So we got another device we use to do that with. Okay, does that make sense? And this will make sense when we look at that.
So the vacuum don't turn on and off.
Yeah. And so we're not concerned with the flow, we're concerned with how much vacuum we have, right? That makes sense. So this is a flow control valve. This is what's moving it that way. This is a magnetic sensor called a Hall effect sensor we'll look at. This is part of circuit 4. Y'all understand? So this guy here, and this will probably make a little more sense. So this guy consists of 4 circuits. Circuit 1, and for every circuit, you have control and you have a load, right? You understand? That makes sense. So this is a 4 circuit layout for pneumatics. So the one on the left, everything that belongs to this, they're calling, it's got a number of what? 1. This is the second circuit, it's got a number of what? 2. This is the third circuit, so everything that belongs to this circuit starts off with a 3, right? And then we have 4 circuits, so everything that belongs to that circuit, the number is what? 4. Does that make sense? Now, that first sensor is not part of any one of these circuits. So it's called what? So it's called B1. So it don't have a 1 to start off with it. So basically, it's not part of one of the 4 actuator circuits. It's independent, right? Everybody else? Because it's not an actuator, it's a sensor. That makes sense. And so all your actuators are B. If it's part of a circuit, it goes what? It goes number, what it is, and then the number inside that circuit. Y'all understand? So 2, and we start from the control valve up. So notice this is labeled what? 1. All these are labeled 2. That's the second thing we see. Your load is going to be the very highest number of the circuit. Does this make sense? Everybody okay? So here we have 4 circuits, and that's what this shows. So we have, actually we got 5. We have the power circuit down here, and notice it starts off with 0. Okay, because it's not an actuator circuit. So 0V, this is our disconnect right here. Then this is our service unit. So this is a filter. So that's the little glass unit right there. This is the pressure control valve. So this guy here doesn't control the flow. It controls the what? The pressure. And we should have that set to 50 psi. This is a power source, by the way. So one of the tricks they did, and one of the things when you go through troubleshooting, once one of your first things is to pull a visual inspection, right? And then the next thing to do is to verify power. And of course, on these we have a fluid power and we have electric power. If either one of those powers are not working, then the section's not going to work. But the problem you have is people think about checking to see if the electric power is there, and they forget to check what? The fluid power. If nothing moves, and they're over here taking voltage measurements, and they skipped over one of the basic rules before they take any measurements. One of the first, within the first 3 steps, is to verify what? Verify power. All power sources. All sources of power. Of course, what do you think this is a symbol for? It didn't look. That's a gauge. Okay, so that's the pressure gauge that's part of the service unit. Then we move up here. So this is circuit 1. It consists of a directional control valve. Okay. It's a four-way 2-position valve. Now the way it's nomenclatured is kind of weird. They say a 4-2-way valve. So they say, even though 4 is, when they talk about the ways, that's the number of what? Ports. That makes sense. And we've got stuff hooked up to it.
I mean, for the most part, though, isn't 4 pretty much pretty consistent?
No, well, it depends. It depends on the number of positions, and of course, how many exhausts does it have? Most of the time, when you got like a 3-way valve, you have 2 exhausts on each end. If they combine the exhausts, then usually it would drop off.
I never saw one more than 4
5. So if it's got an extra exhaust, it could be a 5-port valve, and it would have 1 exhaust per outside. Is the way this works. In fact, they label some of these, and some of the labeling when we go in and look at parts, they label some of these as 5-way valves. But I didn't find any on the diagram that showed 5 ports. But we definitely can look at the Festo. We'll look at the Festo, and they got some 5-port valves. But 5-port valves it has what? It has 2 exhaust ports. And they do that for one thing so it don't share, and a lot of times it makes the valve operate faster than trying to share exhaust ports with a lot of different things. Our exhaust port is not actually on the valve itself. Our exhaust port is right here. So this is the exhaust port right here. Y'all understand that? You okay on that, Bob? You have? And of course, this is the symbol for pressure. So notice these arrows are pointing different directions. So this is our source. By the way, all these symbols would be basically the same for hydraulics, except all these symbols would be black. They would be colored in. So if they're opened up like this, it means it's definitely pneumatic. If they're colored in, it means it's hydraulic.
What situation would there be which I've never seen it myself, but I was told that they control the flow with the exhaust?
Well, the problem we have with pneumatics is that pneumatics are compressed. And if we control the flow coming into the cylinder, the part that's moving, as soon as it moves, we have to recompress the air. As soon as it moves, we have to recompress the air. So what happens if we put the flow control on the input on a pneumatic cylinder, the cylinder is going to jump. So pneumatics, we put the flow control on the output, right? You understand? So that way, when this guy here is pushing, all this air is trying to push, and it goes to the flow control valve that controls the flow. So we call that meter out. So if you put your flow control on the exhaust, it's called meter out. If you put the flow control on the input, it's called meter in. Hydraulics, it makes no difference.
That's all.
Hydraulics makes no difference. Pneumatics, we meter out. Because if you meter in, the cylinder, when it moves, it's going to have to do what? It's going to have to recompress the air. And it's going to move and recompress the air. So if we meter in on a hydraulic cylinder, you'll notice, and we might try that over here. you'll notice that the cylinder jumped.
Well, what about on double axle?
Well, double axle cylinder you meter out, but we use 2 flow control valves.
Oh,
Yeah, so this is 2 flow control valves. But if we look, and this is I don't think I've got that in this slide. Let me look real quick. I know it's in the other slide. And of course, we identified the circuits, right? So we got 4 circuits in here. The first one on the left, and this is usually laid out according to where you run into. So we know that circuit 1 is probably going to be on the left side of the module. Circuit 4 is probably going to be on the right, or further. I don't think I put that here. No, I didn't. So let me go into the, this gives you, a lot of people don't understand these valves. So what you got to do is you literally, and I'm proud of this, by the way, I did this myself. So. All right. Because I didn't get here in after. Because I had the help desk this morning. Did you read your email? And plus through, I don't know where he's at. Let me pause. So the position is usually drawn at its at-rest position. These are the symbol for the solenoids. Now the solenoids, when we activate this one, it's going to push this symbol to the right. When we activate this one, it's going to push it to the left. This is a symbol for a mechanical override. Just about all industrial devices have the ability to override them. Now this is a power source, so when you do this, you need to make sure you understand the consequences of causing something out there to move. Right? You understand? They showed a video I was looking at the other day where it was in a bottling company, and they had a problem where a bunch of cases fell off and broke a bunch of glasses and was under disunion. And they sent a guy under there to clean it up, and they didn't lock anything out, and one of the operators come over and pressed it and lowered that thing down. So the consequences of what's going to happen when you do that, right? So right now, the flow control, this is a check valve. And the check valve only lets something flow in one direction. And it's opposite of the arrow. And what you're visualizing is when the pressure comes up, it's going to unseat that little ball and let it come through. When the pressure comes through on the other side, it's going to seat the ball, right? You understand? So right now, we're not going, this is the flow control valve right here. So right now, the pressure is going up, right? You understand? It's coming up here, and it's doing what? Pushing it this way. My exhaust is coming. It's going to seat the check valve. It has to go through the flow control valve and back out to the exhaust. Okay. So it's going to push in this direction. Okay. Now, when we switch the valve, so what you got to imagine in your head on this, and this gives people problems, they see that symbol, as this whole symbol down here, when this guy here activates, it's going to push this whole symbol to the right. So when I activate 3M1 over here, so right now we're activating what? 3M2. Okay, so this is activating 3M1. So the whole symbol did what? Shifted. Now what happens? Now the pressure comes in, does what? Bypasses this, unseats this. It's going to take the path of least resistance, right? You understand? Here it's choked off. Here there's none at all. It's going to go this way, come over here and do what? Push the actuator that way. The exhaust is going to come through. It's going to seat the check valve, so it's got to flow through the what? Through the flow. And this is what we mean by meter out. So what we're doing is we're metering the exhaust. And we do that in pneumatics. Why? Because as soon as that actuator moved, the air would uncompress, and then what would it have to do? It would have to compress it. Right? You understand? So if we metered in on a pneumatic, it would be jerky. The cylinder would be jerky. Hydraulics doesn't make any difference, because hydraulics is uncompressible. So you can meter in or you can meter out, which one is preferred with you, whichever one your plant decides to do. Pneumatics, we meter out. That's what that term means. Meter out means where do you put the flow control valves?
on on 3D2 and 3D3, what's controlling the arrow valve?
These are not valves. These are sensors. These are your flow control valves right here. These are manual. You have little knobs on there you adjust for what you want the thing to run. Now we do, these are very, very popular. They do have what they call proportional valves, where you can literally adjust the flow. Those are analog devices. Those are not digital devices. So you might run into those. If I need to vary the speed, then you would go into a proportional control flow control valve. Normally we do it manually.
Aren't flow control valves though, aren't they one direction?
No.
Oh, they're not?
No. And that's why in hydraulics, we'll put it on one side, and they won't be directional. So on hydraulic, we'll have a flow control valve over here on the exhaust or the input. Now, if we want it to move fast in one direction and control the speed in another, then we will bypass it. We'll use a flow control with the check.
So
if we want it to move the same speed in both directions, which is almost, we want it to move the same speed in both directions, on hydraulics, we'll just put a flow control valve. We won't put a check valve.
So what causes that to not go to the flow?
Because it takes the path of least resistance.
So once that check valve opens.
Yeah, once the check valve opens, so then you got zero opposition here, practically zero opposition here. You got, so if I was a short circuit, so if I put a wire around a 100 ohm resistor, how much current is going to go through the 100 ohm resistor? None, because you got a straight piece of wire. So I can go this way and have no resistance, or I could go this way and have 100 ohms. There's actually 0 volts dropping there. And there'll be no voltage drop across the wire. So that wire has no resistance. It won't drop a voltage, so your resistor will not even see a difference in potential. If we don't have a difference in potential, we don't have current. So this is exactly what's happening. It's exactly the same way.
So, but initially, when air goes to there, it'll go through the flow control until that check valve.
Yeah, which is instantaneous. Okay. I mean, we don't even think about it. Now, sometimes it does create a little pressure. Sometimes if the check valve is not going to be oriented right, then they'll put a spring up there to make sure the check valve closes. And if it's got a spring, spring in the check valve, then there might be a little flow through there, but 99% is still going to go through the check valve. So it's not going to affect the flow. That makes sense? Okay? So y'all understand the difference between meter in and meter out. I did this, by the way. So what we do when we meter out, we control the exhaust. And like I said, in hydraulics, if you're going to do it the same speed in both directions, you won't have a check valve. It'll just be a flow control valve. Because no matter which way it's going, whether it's going to be from your, we don't call it exhaust, tank, on your tank side, it will have the same pressure as your other side.
Right.
On the other side, on the other side of the flow control is where it would be extremely low. But what you got to imagine on these hydraulic valves, on these fluid valves, and this is true on hydraulics too, is that they'll draw the symbol in its at-rest position, right? You understand? And you got to visualize it doing what? Shifting it. Notice the ports don't move. By the way, you notice the odd numbers, the way they number these things, the odd numbers are on the source side, and the even numbers are on the load side. So we would call this, so this is electrically pushed, right, with a solenoid. What's this? That's manual override. And they're not easy to get to. On a lot of relays, they're real easy to manual override. These you usually have to have like an Allen wrench or something very small to get in there and push on.
Well, they had something happen last week. Talking about the vacuum grippers. They got one that's got probably hundreds of vacuums in it.
Yeah, it's a vacuum surface, yeah.
Well, somehow somebody in there in the breast of manual activated water and so when it was all of them sucking up, you had one blower. Something to that effect. And they spent a while trying to figure out. I asked them what ended up being the problem. And they said somebody activated, somehow manually activated vacuum something and reversed it, basically.
Okay, guys, so let's look at some of the symbols. So the first symbol, the arrow pointing toward the actuator, that's your pressure source, right? And then we have what we call a service unit. Service unit it's got a different symbols, but it contains more than one unit. Of course, this is a symbol for a filter. This is it's a pressure control valve, right? And then, of course, this is a gauge.
Did you just say that the direction of the arrow and the gauge indicates something?
No. Okay. This is the only symbol I've ever seen. It doesn't tell you what type of gauge it is. So we have flow control gauges, and it's just some of those things. They usually got to label them or tell you what they are. So a flow gauge would tell you the speed of the fluid. You won't run into that often in pneumatics. Pneumatics is really, really great, but it's hard to control the flow because it uncompresses and compresses. Hydraulics, though, you can control the flow of hydraulics down to whatever you want it to do. As long as it's below the range of the flow of the pump. So the pump's running at the same speed, so it's going to give you the same flow. Compressors run at the same speed. Most of our compressors, continuous duty compressors, give you a pretty constant flow, but they're very, very, very expensive. So most of your shops and stuff, they're going to run a tank or tanks. And so what they do on a tank is they use an intermediate duty motor, and they do what? They run it up to a pressure, and then they run it down, and then it'll compress up to a certain pressure, and then it'll drop down. So your pressure's changing all the time, and when your pressure's changing all the time, it's hard to really get a really good control of the flow.
I remember working bus tank. We had to have 600 PSI to go on.
Yeah, that was a high. I never run into things that ran at that high pressure, but that's what they were running up at the Goodrich plant. That would be a Goodrich plant. Their high pressure was 600. Because they're making tires. Some of the things that when they come in and clamp down and reshape that tire and stuff, it's. But that was their highest pressure, 600 psi. And that's really got to be treated, guys, because air can only hold so much moisture. And the problem is liquids don't compress and air does. So in the amount it holds depends on the amount of cubic feet. So what happens is that when you compress air, it can't hold water anymore. So what does it do? It releases it. So if you're going to run pressure that high, you got to have all type of moisture removing devices out there, using chillers and all kinds of stuff. Yeah.
What does PSI mean again?
Pounds per square inch. We have two methods of representing pressure. We have over here at the U.S. we're still using PSI, which means pounds per square inch. But if you get anywhere else, they use something called pascals. And I think it's like 14 point something PSI per pascal. So normally you're going to run into K pascals. No, that's we have different types of gauges. We have some relative to atmosphere. It's just another way of representing pressure. We have different ways we can reference the pressure too. We have great gauge pressure. We have atmospheric pressure. So when you get pressure, you're going to have to reference it to something. Does that make sense? So what is zero? So we have different ways that we can refer out. We got what they call absolute zero, where you actually create a vacuum and you reference it to that, which will give you a perfect pressure. So if we represent what we call atmospheric pressure, all our pressures are actually about 14.7 psi off, because that's how much atmosphere is pushing, right? Does that make sense? And then gauge pressure, I don't remember the difference, but there's several ways we can reference what we're starting our zero from. Do y'all got any questions on this? By the way, if we look at this, this is these are our symbols. I'll give these off code for you. If you was in, if you had blueprint readings, y'all probably went over it. And then if you take the fluid power class, or we call it hydraulic pneumatics here, that would be the same thing. Some of our cylinders, this is a symbol for a vacuum generator. So this is basically uses a technique called a ventura, which they put pressure through that. They have a real narrow place. So it's basically like an airplane wing, but it's on both sides, and if it floats through there real fast, it creates just like an airplane. So when it crosses across the top of an air wing, it creates a low pressure. And the bottom of the wing is flat, which is creating a high pressure, which causes the plane to fly. Well, what we're doing here is we have two airplane wings pointing down. So the air flows real fast through the ventura, and it creates a vacuum. And then this is basically where they do. So the vacuum comes over here. So what this means is we can create a vacuum without having a vacuum pump. So this is very, very popular, and this is the same thing they use on both lines. Best of line. This is a silencer. Its technical name. Most people call these mufflers. These are on the exhaust port because when these valves shifts, it would release, and it does the same thing as your car muffler does. If you ever strip the car muffler apart, you see it's just a bunch of vanes in there causing this pop to take all different directions. And so what happens is that instead of it being delivered as a pop on your exhaust, it's delivered over time. So the sound wave is spread out, right, to understand. Of course, now they'll have a catalytic converter in there, but if you look at the exhaust. So these are silencers, and all it does is, you can see what it does, it just makes the air follow a different path, and it's not delivered as a pop. This is a rodless cylinder. So these guys don't have rods. They attach different ways. So whatever you're trying to move, attach different ways. The ones that we have, so they'll have a belt run through here. And then the belt will come over here and roll across the top, and then a cradle of something will be on that belt. Will be attached to that belt, to that wire. The ones we have use magnetics. So the piston it's just a big magnet. And then a very strong magnet, and whatever we want to move is just out here on the outside, and it just attached to it magnetically. All the rodless cylinders that we have on both lines work on that concept. What's nice about a rodless cylinder is that it moves, it creates the same force in both directions. These guys, by the way, the amount of force that we generate, which determines how much of a load we can move. Anybody know the formula of force is equal to area times pressure. Well, you notice on this one, we lose the area of the rod. On this one, we don't. So this guy here would actually create more pressure more force when you extend it than when you retract it. And you'll learn how to calculate that if you take fluid power. So a lot of times retracting doesn't make any difference unless the actuator is moving something in both directions. That's when it becomes critical. Well, we don't have to worry about that on a rodless cylinder because the area is the same on both sides. Pressure regulator. This is a digital sensor. So you guys get confused. We're looking for this arrow right here for a pressure regulator, Of course, this is a one-way adjustable flow control valve. So normally on this schematic, on this diagram, they call them all flow control valves, but actually they're one-way flow control valves because they include a check valve in there, right? So normally when we use the term flow control valve, we're talking about one without the check valve. This is an adjustable flow control valve. So all ours are adjustable. Okay. This is a symbol for what? Suction cup. These are the two symbols they have. So this is the way it would be worded. 4-way, 4/2. So 4 is the number of what? Ways. Okay. This is the number of positions. And then normally what you'd put is the rest of information. So this is solenoid activated, right? You understand. And a what? Spring return with a manual override. So that would be the whole designator for that valve. This is a 4-2-way valve, solenoid activation and what? Manual override. So notice on this one, we use pressure to do what? Move it in both directions. We use solenoids to move them in both directions. And this is a quick exhaust valve. So when we start looking at these diagrams, we'll see all these different symbols. Now this doesn't have a quick exhaust valve, but it does have a what? It does have a vacuum generator. It does have a what? Suction cup. This guy actually has a silencer on it, or a muffler on it, and we can see that when we go over and look at it. This is the pressure valve. This is a pressure control valve. We're using that to control the vacuum, because the pressure is directly related to the vacuum, right? So we can use this. This is a pressure switch. I'm sorry. It looks like it's got two types. This right here looks like we can adjust where it's this is the adjustable pressure switch, and this one right here is not.
What's the symbol inside?
This one, that's a symbol for this. I'm sorry. Oops, wrong side, Rich. So what it is, it's got a single pole double throw switch in there. So one of them would be designated normally closed and one of them would be designated normally open. So that guy would have quite a bit of wire connections available to us. So when we look at our sensors, none of ours have that. But when we look at our sensors, the color code for sensors is set up for 4 wires. And the only difference it is if you have a single pole double throw switch in there. Most sensors are either going to be normally closed or normally open, but you can buy them with both on it. So good question. Any more?
You said that the even number on the diagram.
Right in here, we're talking about this. The even number is on the low side, and the odd numbers are on the pressure side. Are we okay?
So do these carry the same classification as the hydraulic?
Same, exactly same. Huh? I don't know. The letter designator, I'd have to go back and look at that. I know what you're talking about. P for pressure, and then more and more the numbers are becoming more common because they apply to both pneumatics and hydraulics. AB for port side, yeah, I'd have to go back and look that up. It's been a long time since I taught that. Any more questions? Yes or no? So y'all understand the circuit? So it's a lot like electronics. So all circuits in electronics, we know we got to have a source, conductor, and return. We got to have a power source, and we got to have a load. That's the minimum requirement. Normally, normal circuits have a power source. It has some type of control device, so you can control the flow, right? You understand? And then we got a load. And I'm sorry, conductor.
These show that all the exhausts have a common.
Yeah, so they're in a manifold.
Is that normal?
Yes.
Why would they not?
Well, it depends on. Well, what we're trying to do is save as much money as we possibly can. So you got 5 or 6 valves that's going to be located together. So why do you need a silencer for all of them and an input on all of them? So what we do is most of your valves that you buy now, they can come standalone, or they leave off the bottom and you can mount them on the manifold. When you mount them on the manifold, they share the pressure and they share the exhaust. So automatically, that's going to save a lot, right? You understand? It's going to cut down on the amount of maintenance, because now you're not dealing with 8 pressure hoses trying to figure out where they go. So what you do, and if you go over there and look at the big FANUC, all the controls on the side is on a manifold. And you look at all these over here, all of them are on what we call a manifold. Festos are kind of different than most of them. The Amatro uses, of course, Festo uses this. That let's go look. Let me pause this. So instead of getting up here, these are our electrical sensors. Probably need to make little notes on the handout that I gave you. First, if it's a solid state sensor, the standard symbol for a solid state sensor is this square. And then they put this symbol inside. Can y'all see that? The little diamond shape. Y'all can look at it. This is your electrical. Okay, this means it's a solid state sensor. This little symbol down here indicates this has a normally open contact, so it's a normally open contact inside there. Okay. Right here, these are some of the symbols we can have. So notice down at the bottom, if I get in here without pausing the lecture. So if you see this block and see these symbols, so these two symbols combined means it's
So a diamond within a square.
yeah. And of course these are the pins. This tells us what type of sensor it is. And so what I did here is I included this over here. So if I see this solid block, this means it's what? An inductive sensor. If I see this little symbol right there, it means it's a capacitive sensor. If I see this little symbol right here, it means it's an optical sensor. This right here means it's a magnetic sensor. This is ultrasonic. This is the type of contacts we have. So our normally closed contact is a little different than what we learned in motor controls. But notice it shows the switch. So what does an inductive sensor do?
It can,
Not an inductive sensor.
no.
Yeah, so an inductive sensor can only sense metals. Ferrous metals too. I'm in the wrong PowerPoint. That's okay. It's the same thing y'all got. Okay. Ultrasonic sensor is going to be used to sense distance, right? We can use it as a presence sensor, but this guy here is sensing difference. Probably a level or height would probably be, so in our situation, it's sensing height. So it's seeing if the part is what? Too small, or if the part is too big. But we can use these for a lot. These are photoelectric sensors. So these guys are going to use light. We're either going to break the light or reflect the light. And we have a lecture on sensors. But these things sense by light. By the way, proximity. Proximity is a sensor that senses when something is at a certain place. So it's not a position sensor. A position sensor sensors where it's at. A proximity sensor sensors when it's at a position. Is that proximity? So a limit switch is a proximity sensor, but the limit switch is kind of like when operating systems first came out, we call them DOS, or disk operating system. Now this became known as the old text-based command prompt operating system. So when they came out with another operating system, even though it was a disk-based operating system, which means it's loaded off a disk into memory, they call that Windows. So limit switches have been around for years. So the differentiation is there, even though a limit switch is a proximity switch, we call it a limit switch. All of these solid state sensors we call proximity sensors. So normally when we use the term proximity, it means it's probably going to be solid state. Limit switches are the old mechanical ones that's been around for years. And it's the same thing that happens with DOS. So we've been using the name limit switch for so long, it would be stupid to change it to what? To proximity. Because everybody knows what a limit switch is. So a proximity switch means these guys are looking for parts to be at a spot. So that 1B1 is looking for a part to be sitting right there on top of it, right? You understand that B1. If the part wasn't there, it says it's not there, or if it's black.
So what is the Hall effect?
Hall effect sensor, it senses a magnetic field, but it's solid state. Well, all those sensors that sense the position of these valves. Okay. We have two things that sense a magnetic. Now notice we don't call this a proximity sensor. We call it a what? It's a reed switch. Yeah, I was looking at this one, sorry. This senses a magnetic field too. See the little symbol right there? But the way a reed switch works, and when we go over sensors in more detail, I'll bring one here and show it to you. It's just inside a vacuum. It's got two little contacts that are together, and when you put a magnetic field, it closes. So a reed switch is electromechanical. So it's a lot like a relay, but the magnetic field is provided by a magnet instead of a cylinder. These guys usually don't have any adjustment on them, so they will sense depending on where you mount them, how you put them. The advantage the reed switch has is it's very cheap.
I notice it's strong with a normally open.
Well, it depends. You can buy them either way. I've never seen a normally closed reed switch. Every reed switch that we've had and we've played around is normally open.
Seems to me that would be the more logical.
Well, it depends on what it does, and we'll see some of the situations, some of these sensors, and you're right, but some of them are normally closed. Some of them actually have a single hole double throw, so you can actually use the normally open or normally closed or use both. But I have never seen a reed switch. I don't know how it would work, because what happens is it's got two metal rods coming out. And what happens is when you put a magnetic field, well, actually, basically, you put the magnet in there sideways. So one side is the north and one side is the south. But what happens is the magnetic field concentrates through both the switches, and the switches actually pull themselves together. So when you put the magnets up there, you don't want to put a north pole, and you don't want to put a south pole. You want to put a magnet in there sideways so you see a north-south. That makes sense?
Which you may not know this. On the carriers that I work on, they've got a speed sensor which ties into control boxes. And they actually have, all they do is stick a magnet, either a north or south pole magnet. When that speed sensor goes by, it flips that speed sensor. What kind of switch would
That could be a reed switch, and what they're probably doing is the PLC. They know the size of the magnet. If you know the size of the magnet, and when the thing moves by there, it's going to open and it's going to close. And probably in their PLC, they probably just got a timer circuit in there, and the timer circuit, then they say, okay, if it lasted 3 seconds, you had to be moved by this fast. I imagine it's nothing but a reset or a Hall effect. What's nice about a Hall effect? What's nice about a Hall effect is a Hall effect usually, sometimes you can set the sensitivity on a Hall effect. You can't set the sensitivity on a reed switch. Because a reed switch is electromechanical. But it still senses a magnetic field.
Well, that's what we think about.
A Hall effect you would put north side, you would put either north up or south up. It don't really make any difference. Well, that's not true. It depends on what type you got. So a lot of times a Hall effect, we call it a latching. where a south pole would make it latch, and then a north pole would make it open.
That does make a difference.
And then the length of the magnet, so the north will be on this side and the south will be on that side, and you literally can time. They could literally time off a Hall effect.
They use the south pole to slow it down. Yes. Use the north to speed it up. And what it is, when the carrier gets into a long stretch and wants to go faster, it'll go past that magnet and speed up. Well, when it gets about 7 or 8 feet from the end of that line, it goes past the other magnet and slows down to make the turn.
Well, it's probably a Hall effect. It's probably what they call a latch and Hall effect.
Because the buffers sit there and S like 6 times. They've got those switches everywhere.
Capacitive sensors can sense solids or liquids. So capacitive sensors are basically what can sense about anything. Normally we use capacitive sensors to sense non-metal parts. So even though they will sense metal parts, we usually use inductive sensors for metal, and then that way the inductive sensor ignores everybody else. Right, you understand? And then we use capacitive sensors to sense everybody else. And this is a what? That's an indicator lamp. Everybody okay? This is a limit switch. This is a selector switch. Don't know what a selector switch is. That's that reset switch over there. So you got 3 positions on that. You hit it to reset. Then you got manual or you got what? That is what a selector switch is. So a selector switch has multiple positions. But it's only got one, and it's got a D10. This is a solenoid, but when we look at the electrical prints, so when I look at the pneumatic prints, it's going to draw this thing right here, right? You understand that? When we look at the electrical prints, this represents the valve, that little butterfly thing. That means that's a valve. So this is not drawn on the electrical prints. Right? You understand? It's just like when they do the solenoids, they don't put the wiring for the solenoids, they just say that's a solenoid. Well, what they do over here, this is the symbol of a solenoid, and if they come up here and put this little dash, that means there's a mechanical connection, and this is the symbol they use to represent the valve. So this would be a single acting cylinder because we got one solenoid. Notice this one, it's got 2 solenoids, and in the center it's got the valve. Both of them's got mechanical connection. So that would be your double acting cylinder. This is the symbol for a momentary contact push button. So this would be like the start button over there, right? This is the symbol for your e-stop button. So it's got a detent in it. Now what does a detent mean? A detent means that it holds the position. Okay. And then this little square without the line is a relay coil.
Back on capacity, how does it protect it?
What it does is, the way a capacitor works is, if we draw it like this, it makes more sense. The way the capacitor works is we basically have 2 metal plates. And then what happens is that we electrically make a circuit through here with an electrostatic field. So you got to put AC on it. So the capacitive sensor and the inductive sensor works off AC, so there's an oscillator circuit. Now what determines the amount of capacitance is what you put in the center of those 2 plates. And we call it the dielectric constant. And it's all reference to the dielectric constant of a vacuum. So a vacuum would have a dielectric constant of 1. Then everything else is going to conduct some electric. It's going to change that field. So whatever moves into that field changes the dielectric constant, which means it changes the opposition of the flow in and out of the capacitor. So whatever it is. So glass would have a dielectric constant. Plastic has a dielectric constant. So normally what you have is, of course, so there's more to it than just this. There's a lot of electronics. But what you have the ability to do, even on your light sensors, it's just about all your light sensors are going to have a sensitivity adjust on there. So that means if you wanted to detect water but not detect glass, then odds are you could adjust it and make it do that. But if you set it at glass and water's dielectric was between there, then it would detect glass too. Does that make sense? So you can't really make it detect a object unless it's the only object that it'll see. And that's the way it does it. It changes the dielectric constant. I can go over there, and if we got time, we'll go over there and look at that. And I can take two wires and put them together, just like this, and put AC on them, and put a scope on there, and put a resistor in there, and I can take a plastic bottle on there, and you'll see the output change. I can take a piece of metal and put it on there, and you can actually literally see the output of the capacitor change depending on what I use as an insulator, which is pretty neat. And these guys here work exactly the same way. So there's a lot to these sensors. We don't need to know what's inside there and exactly how they work. All we need to know there is what they do. So what does a capacitive sensor do? Well, it has the ability to select to see both solids and liquids.
Okay, if you go out and buy one, do you have to specify you want one for solid? No.
All you have to do is specify. Usually they give you a dielectric constant range, so you would have to know what range it does. It's going to see multiple things. So you just can't, as far as I know, you can't have a capacitor sensor that senses nothing but glass, unless you had the ability to set an upper and a lower limit. So I'm not saying I've never seen one, but I can see it happening. So, but you'd have to have two screws on it, right? And then you would have to put what you wanted to in there and adjust one, and then put everything else you wanted to detect, and you might be able to do it that way. Good question. You more? Are we okay? So the little problem that we ran into is that, so this is the electrical diagram. So a PLC is made of nothing. So this is the PLC. So PLC has ports on it. We have input. So if it says I, that means it's a watt input. And this identifies a module number. The Siemens PLC runs in groups of 8s. So the Allen Bradley the modules can run in groups of 16s. So that means I can buy a module that has 32 inputs, but it would take up 2 module numbers. Does that make sense? The Siemens runs in groups of 8s. So the first group module would be 0 to 7. The next one would be what? Yeah, but 8 to 15. We can see that when you look at that. This is what we call syncing, because if you notice, so the device that provides the voltage, we call that, and we know a circuit consists of several different things. First of all, we got to have a source, right? And then we have to have a load. Everybody understand that? Okay. So if we look here, notice that all the push buttons are connected to the positive power supply. And we call the positive power supply, we call that the source, right? Everybody understand it? So the term that we would use is we would say all these guys are sourcing because they're providing the voltage. So what the PLC is providing, it's providing this guy right here. So the PLC is using a negative common. So we would say the PLC is syncing. Does that make sense? So the device that provides the ground or the minus DC, we say that is syncing. The device that provides the positive DC, we say that is sourcing. So these switches are hooked up sourcing. So that means the PLC needs to be hooked up syncing. Now this is a term they pulled in from digital logic. So this, when you take digital, if you've had digital, we'll talk about syncing and sourcing.
In detail.
And that's basically, it's still true on the PLC. So when we provide the voltage, we call it sourcing. The device that provides the ground, we call that syncing. So the two output transistors in a logic gate, we have a sourcing transistor and a sinking transistor. And that's exactly where these terms come. Sometimes it's configurable on the PLC, sometimes it's not. The Allen Bradley allowed, on some of their PLCs, they allow you to set them up as syncing or sourcing. On your modular PLC, which means you have individual modules that you plug into it, you buy either sourcing or syncing. Rule of thumb, though, is inputs are syncing and outputs are sourcing. But these are all inputs. Over here. So over here is typical. Now, it all depends on what type of sensor you got. Syncing and sourcing only comes into play with DC. So if you got an AC PLC, you got AC inputs, AC outputs, it means nothing. Syncing and sourcing only comes in with DC PLCs. And it all depends on what type of sensors you buy or they use. And if you take solid state, you'll understand that. But we have two types of solid state sensors. We have one called PNP, and we have one called NP. And the easy way to remember, P means positive. So PNP sensors are sourcing. NPN is syncing. So that means if I have syncing inputs, I've got to hook them to a source. If I got a syncing device, I have to hook them to a source. So remember that. Because when you buy these sensors, you have to, and that it'll be listed either NPN or PNP or syncing and sourcing. Most of the time they do PNP and PNP. But P starts off with a P, right? So if it starts off with a P, it's what? Sourcing. If it starts off with an N, it's syncing. So, well, that's the same. But the problem is that the term is syncing and sourcing. So when you buy these inputs, if you got a modular PLC, and if you get into a big company, you're going to run into modular PLCs. That's the way you buy the DC input modulars. You buy either a syncing input or you buy a sourcing. So this is the guy we wanted to come in. So these are. By the way, this is what concerns me. Normally, if we see two wires coming into it, these are magnetic reed, because they don't have to be powered up. They're not electronics. They work off a magnetic field. If we see three wires coming into it, these are going to be Hall effect. And we'll make sure we look up the part, because some of Siemens got a bunch of parts labeled wrong. They got these guys labeled as reed switches, but reed switches don't have to be powered. Okay, y'all understand? Hall effects are electronic circuits. They have to be powered. So powered sensors are going to have at least what? 3 wires. Okay. The ones that are not powered will have 2 wires. So these would be reed switches. Reed switches don't have to be powered. They operate off of a magnetic field, right? Understand? Yes or no? This is the terminal block right here. And then this right here is the cable. So there's those terms right there they're using for the terminal block. So it looks like they're using XC1 for the cable and XTB1 for the terminal block. Are we okay? This is the one I wanted to show y'all. So here we go. So here's that little pressure switch we were looking at over there. That's that little red pressure switch. And it's called what? They're calling it 2P1. Because it's a switch or pressure. So this is not labeled because it's not part of the hydraulic circuit. Right? I mean, I'm sorry, the fluid power circuit. And this is, so there's that other sensor. What's this one? That's B1. So that's not going to be on there either because it's not part of the pneumatic circuit, right? So B1 is your what? Or it was on there, wasn't it? So the only one that wasn't on there is this 2P1 right here, which is that. Are you okay? So these are all this is the electrical. And of course on here, the only thing that's electrical about this is the PLC. If we see 3 wires, it's a Hall effect. So this says it's what? By the way, Siemens puts this, I guess it indicates north-south. See, they got this side of the magnetic not colored in, and this side is not. That's still magnetic. This guy only provides a normally open contact for us. So when it's false, the contact is open. When it's true, the contact is closed, right? Y'all understand that? You gonna go to sleep, Larry?
I'm fine.
This is the e-stop button. Are we okay? So this is what I wanted to make sure we understand, because this guy right here was not on our prints that I gave you. And that's what 2P1. All the rest of them is, because these are part of the hydraulic circuit, or the fluid power circuit. And Larry's got me saying hydraulic.
Well, that last, I mean,
Yeah, this is what we just went over. Yeah, so it's, yeah. And that what, I didn't look to see if it went off, but it was true when it picked up. And undoubtedly the PLC, once it says it's true and it goes to the next step, then it's not going to, Oddjar is not going to look at that sensor anymore. Are we okay? So are we ready?